Welcome back. In this video, we're going to perform another example of a two-sample t-test. We will also look at the requirements needed for the conclusions from this test to be valid. A plant physiologist conducted a study to determine whether mechanical stress can affect the growth of soybean plants. Young plants were randomly allocated to two groups of 14 plants each. Plants in one group were mechanically agitated by shaking for 20 minutes twice daily, while plants in the other group were not agitated. After 16 days of growth, the stem length of each plant was measured. All right, so we're going to compare the treatments here using a t-test. Particularly, does the stress imposed on the plants affect their average stem length? You can see that we have the sample data here. We're always going to have the sample size, sample mean, and standard deviation. When we do this in the lab, you'll actually have the raw data instead of just the summary statistics. The first step that we need to do is, before we determine the hypotheses, we need to actually verify these requirements or assumptions. These will sound familiar because these are all based off of the first set of requirements we ever saw with confidence intervals. Namely, we need randomly and independently selected samples. There's another way that that can be satisfied, however, and that's by having a randomized experiment where the units are randomly assigned to treatment groups. The observations must be independent. And lastly, we have a normal requirement distribution, and that can be satisfied in one of two ways. We can check manually with a QQ plot to see if the samples are normally distributed, or we can see if they have a sufficient sample size. Do you remember what that sample size is supposed to be? It's at least 30. Now, it's not required that the sample size be 30. That is a backup from the central limit theorem. Let's go through these requirements. This first requirement about random selection, well, you can see that in the description of the example, we have a random allocation of the plants to the two groups. So we have met that requirement. Also, it does not appear that the plants were paired in any way. So I think it is fair to assume and safe to assume that the two samples were selected independently. For the second requirement listed, the individual observations should be independent. I think that is a fair assumption that the growth of one plant is not influencing the growth of a second plant. And so that is applied, that property of independence is being applied to the individual plants. The third requirement requires a little bit of work. We need this normal distribution to be satisfied. But we were not given any of the raw data here, so we cannot check if the 14 values from the control group are normally distributed, nor can we check if the 14 values from the stressed group are normally distributed. Since the sample sizes are also not particularly large, i.e. they are not at least 30, we are not saved by the central limit theorem. So in this case, we will have to proceed under the assumption, under the caveat that we will assume that the 14 observations in the control group are normally distributed and that the 14 observations in the stress group are also normally distributed. again, if we had the raw data, we would use R to create and check that the QQ plots are demonstrating normality for these two samples. In our next step, we're going to declare the null and alternative hypothesis, but I also think it would be valuable for us to identify the response variable in this scenario. Since it's been a while since we've considered response and explanatory variables. So what is the target variable that these researchers are interested in about these plants? Aren't they, like, what are these 14 or 28 values representing? It's the total stem length of each plant. So that is the response variable. Let's establish the null and alternative hypothesis. Recall that the null hypothesis is always a statement of equality. And here, what we're saying is equal, or not different, is the mean stem length of these soybean plants, regardless of what group they are in, if they were in the control group or stress group. The alternative hypothesis then is that the mean stem length of the plants in the control group is not equal to the mean stem length of the plants in the stressed group. It is good practice to be clear about what the significance level is. And if we jog back to the example, we were actually not given a particular significance level. I have a note here. Remember the value that is standard practice if it is not defined. That value for alpha is 0.05. In a future video, we will discuss pros and cons of this value, or even why it is considered the default value. Next up, we will compute the test statistic. Hopefully you've got the formula in your notes easily accessible, but here it is just in case you don't. I'm going to scroll back up briefly to take a look at some of these summary statistic values. So the first sample mean I'm going to use as the control group. So I'm going to call that group 1, and I'm going to call the stressed group group 2. Okay, so I got 30.59 minus 27.78, and I see my 2 standard deviations there, and the sample sizes are the same. So I'm going to plug those in to our formula here. Okay, so I entered that all in, and I've typed it into R as my calculator, and I got about a 3.832. So our next step is going to be to determine the p-value here. And we're going to use R to do that. And I always think it's valuable to illustrate what we are doing so that we know what we're doing. So I like to draw a quickie t-distribution. Normal, 0, middle. The degrees of freedom, in this case, I went ahead and used that intense Welch-Satterthwaite formula to determine the degrees of freedom for us, and it was 25. Our test statistic here, kind of a big one, 3.832. We want the probability, the area beyond this tick mark. But we want the probability of observing a test statistic at least as big as the one we've computed. So I also need to consider the negative of our test statistic, and we want the probability beyond that one as well. So we want these 2 pink regions here. Now a 3.8 as a test statistic is quite large, right? That's almost 4 standard deviations away from the center. We're going to use R to determine this probability. Because we want to find probability in the t-distribution, P for probability, we want the PT function. Remember that each of these pink regions is the same. We want both of them. It is easier often to find the one on the left. So I'm going to type negative 3.832, comma, the degrees of freedom, 25. Wow, that's a small number, right? I've not illustrated this very well. This area in the left tail is approximately 0.00038. What property, maybe you tell me, what property allows us to say that this pink region is also 0.00038? Thereby, the total p-value here is, I'm going to double. I'm going to multiply by 2 our previous result, and we're going to get a pretty small number, 0.00076. Now that we have determined the p-value, we are ready for our last step, which is to state our conclusion. We want to compare our p-value with alpha. I have some more notes here. It is often better to, or it's a better practice to state the p-value rather than simply state, we reject or we do not reject the null hypothesis. We're going to demonstrate that, and then we will also translate this conclusion and relate it back to the study variables. Since our p-value is 0.00076, which is less than alpha, we have evidence to reject the null hypothesis. Since we are rejecting the null hypothesis, let's relate that back to these plants that are being agitated or not agitated and their growth. We have evidence for this second statement. So when we translate our statistical conclusion, we're going to mention how the mean stem length is not the same between the non-agitated control plants and the agitated or stressed plants. We might say that the data shows a significant difference in the mean stem length between the two groups, the plants that were agitated or stressed for 20 minutes twice a day, and those that were not. I've got a couple bonus questions here for you. Question: is this an example of an experiment or an observational study? I'm going to allow you the opportunity to answer that. I'm not going to answer that right now. The one that I do want to pose in the question that I will answer is the second one. Suppose that we constructed a confidence interval for the difference in population mean stem length after 16 days of growth. As a reminder, this came from chapter, I think it was 6.7. The question here is, would this confidence interval for the difference in means, would that value contain 0? Why or why not? We don't need to compute this confidence interval to answer this question. We can do it anyways, but let's see if we can answer it without any computation. Remember what we said 0 represents. 0 represents no significant difference. Let's track back to our conclusion here. Our data shows a significant difference. So do you know the answer here? The confidence interval for the difference in the mean stem length between the control group and the mean stem length between the stressed group would not contain 0. Let's set up the calculation for this confidence interval. For it to correspond to our previous work, we would want to use 95% confidence, right? Because alpha was 0.05. I'm going to write this down and then fast forward through this. I'll ask you to think about, where am I getting this t critical value from? I'm going to put parentheses here to bookmark it. How am I going to figure that out? I would use the qt function in R, or I would use the t table. Regardless, you should get the same number, approximately 2.06. So 25 degrees of freedom was given, but where did this 0.025 come from? Since we are using alpha 0.05, that implies 95% confidence, and recall that 0.05 is split between the two tails. This is half of alpha. To determine that in R, 0.025 is in the right tail, but QT needs to consider the area to the left. So I have taken the complement there in the input for QT to arrive at approximately 2.06. This is going to get us the margin of error of about 1.51. Finally, our confidence interval, the lower bound would be a 1.3 and the upper bound would be a 4.32, and the units of measurement here are in centimeters. Now, we didn't need to compute this to answer our question, but hopefully this satisfies your curious mind. We could even dive a little further. Because both of those bounds are positive, we know that the first group, the control group, must have had a larger average stem length than the stressed group. If it was larger on average, well, by how much? This supports that the mu of the control group was larger than the mean stem length of the stressed group by at least 1.3 centimeters and up to 4.32 centimeters. We have done 2 examples of a t-test now. I have shown you an example in which just now the conclusion was a rejection of the null hypothesis. And in the previous video, we did an example in which the result was a non-rejection. hope you enjoy it.